So we turn now to what I think is one of the most interesting questions in nanoscience, which is on what scale do we stop describing a system by Schrödinger's equation, by quantum mechanics, and start to describe it by classical mechanics. There is a formalism for integrating the effect of thermal fluctuations with quantum mechanics called the density matrix formulation of quantum mechanics, and it's described in section 325 of 24 of the book. It allows the time evolution of a system to be described in terms of the way that states are mixed by some time of evolving perturbation. One of the ways in which this difficult set of equations is solved is by the random phase approximation, and this is tantamount in a way to throwing out all of quantum mechanics, because it says the quantum mechanical interference effects over time get smeared out by thermal fluctuations. I like to talk about this problem more qualitatively and try and get some insight using the uncertainty principle. So we can always talk about the interaction between a pair of atoms in terms of this interaction matrix element between the atoms. So I'm showing you the wave functions here, and we evaluate this matrix element corresponding to the overlap of wave functions from both atoms and associate some energy with that. And as you know from what we did in chapter 2, for covalent bonds, this number is on the order of electron volts, or thousands of kilocalories per mole. What happens when we move our atoms very far apart so that this overlap now decreases to the point where gamma is on the order of thermal energy? Well, from the uncertainty principle in the form delta E delta T is h bar, we can derive a time associated with the build-up of the quantum mechanical state on the order of h bar on gamma, or h on kT. And it turns out that for 300 degrees Kelvin, this is around about 0.1 picoseconds. This is about the time scale of thermal vibrations themselves. So, on the time scale that quantum interference effects would develop, the system is moving. Let me illustrate this for you by going to an example taken from chapter 7, which is a discussion of resonant tunneling. So we consider a chain of atoms, and we send a wave packet in, which is a way of describing an electron as something of more of a localized particle. And we ask how the probability amplitude builds up on subsequent atoms in the chain. What we see is that if gamma, I'm going to call this gamma left here and gamma right, the overlap with the chain on the left and the chain on the right, in the event that gamma left and gamma right are very small, the probability amplitude on the central atom becomes very big, but it builds up very slowly. So, if these other atoms are moving on the time scale of that build-up, quantum coherence is destroyed, and with it, in this case, resonant tunneling.